Let us do a small numerical on image frequency rejection ratio alpha, which we have defined in the previous video clip. The problem says in a broadcast super heterodyne receiver, the loaded Q of antenna coupling circuit at input of the receiver is 100. This means the loaded Q is nothing but the quality factor of the input circuit at the receiver is having the value of 100. So the quality factor is equal to 100 is given in the question. The question says calculate alpha, which is the image frequency ratio, at the station frequency of 1 megahertz and station frequency of 25 megahertz. So we have to do the calculation twice. We have to find out alpha for 1 megahertz first and then for 25 megahertz. So let's do that. We know that the alpha image frequency rejection ratio will require two values. First of all, rho and Q. Q is given, rho is something I have to calculate. To calculate rho, I will require image frequency first. FSI is equal to Fs plus 2IF. Fs in this case is 1 mega. If nothing is mentioned, I'll take IF as 455 kilohertz. If its value is given in the question, then we use the given value. This will come out to be 1.91 megahertz. Now I can calculate rho. Rho will be equal to FSI upon Fs minus Fs upon FSI, which will be 1.91 mega upon Fs, for which we have calculated image frequency is 1 mega, minus 1 mega upon 1.91 mega, and this turns out to be, when you take this ratio and when you take the difference, this rho will be equal to 1.386. And once we get the value of rho, and as we already given the value of Q, I can now calculate alpha. Alpha is equal to under root 1 plus Q square rho square. And when you solve this, it will be under root 1 plus Q is 100 and rho is 1.386. So when you take the square root, it comes out to be 1.138.6. This 100 squared is a large value, and the second number that we have is a number greater than 1. So I can neglect this 1, and in that case the square root and square will cancel out. So 1.386 into 100 will give you 138.6. That's the value of alpha. As you can see, the value of alpha is pretty large. That means image frequency rejection at 1 megahertz with the quality factor of 100 will be very good. Now let us calculate the same value for the station frequency of 25 megahertz. So we'll do the second calculation now, at which FSI, which is Fs plus twice IF, will be equal to Fs. Now you can see in the previous case we has taken Fs as 1 megahertz. Now we will take Fs as 25 megahertz and do the similar calculations. So 25 mega plus 2 into 455k will be your FSI, and this will turn out to be 25.91 megahertz. That's my FSI. So rho will become FSI upon Fs minus Fs upon FSI, which turns out to be 25.91 divided by Fs in this case is 25 megahertz minus 25 mega upon 25.91. Megahertz will cancel out from numerator and denominator, and rho will in this case turn out to be 0.0715 approximately. So if you find alpha, again the image frequency rejection 1 plus Q square rho square, this time it will be under root 1 plus 100 squared into, this time rho is equal to 0.0715 squared. Once again, if you work this out, the answer this time will be 7.2, which is also approximately 100 into 0.0715. So the final conclusion is that for the same given receiver, because we did not change the value of Q, we are using the same value of quality factor in both the calculations. So for the same input tuned circuit with the quality factor of 100, when we go from station frequency of 1 megahertz to the station frequency of 25 megahertz, you can see the value of alpha decreases. And this is mainly because of the reduction in the value of rho. In the previous case, the value of rho comes out to be 1.386, but now it comes out to be 0.075. This verifies one very important conclusion, which says that image frequency rejection becomes poor at higher station frequencies. And hence, whenever we test the receiver for image frequency rejection, it must be tested at higher frequencies. If we are able to obtain good image frequency rejection at higher frequencies, then at lower frequencies the image frequency rejection will be only better.